तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, today we shall continue the discussion on I squared L logic circuits. Okay, last class we saw the noise margin problems of I squared L. Okay, see, I squared L was in the 1970s when it was first talked about. Okay, was very popular in the sense that people thought it would be a very popular logic circuit. But it had not happened that way, and the reasons, one of the reasons of course is poor noise margin, but the other major reason is that the propagation delays, okay, have not really been very low. Okay, in those days, okay, maybe 10 nanoseconds was a very acceptable propagation delay, but no longer these days, and it has been very difficult with the original structure to reduce the propagation delays. Okay, one can understand that because of the very large amounts of charge stored in the device. Okay, so we shall, today's discussion we shall take up the propagation delay problem, okay, and see how attempts have been made to actually reduce the propagation delays, mostly with the help of improved technology. Okay, all right. So, the propagation delay of I squared L cells, propagation delay of I squared L. Okay, all right. Now, write it properly, propagation delay of I squared L. Okay, now the I squared L delay, just like as in the delay in a bipolar junction transistor, okay, depends on the junction capacitance, on the capacitances. Okay, and we know that there are two types of capacitances. One is the junction capacitance, and the other is the stored charge capacitance or the diffusion capacitance. So, initially when the current levels are low, it is the junction capacitance which dominates, okay, whereas at high current levels the stored charge capacitance dominates, because the stored charge capacitance is proportional to current, you know that. Okay, so, as you go for higher and higher currents, the stored charge capacitance increases and that starts to dominate. Okay. At low current levels, it is the junction capacitance which dominates, and we have already seen in a bipolar transistor, if you that if you take the current and the delay, okay, so if you increase the current initially, the delay falls and then it saturates. Okay, that is because if you just take capacitance, okay, and find out how long it takes to charge or discharge, you know that basically the basic relation is, if you have a capacitance and Q is equal to CV. So, all right, if you have to charge it through delta V voltage, okay, basically you have to supply a charge of delta Q, all right, and if you are charging with a constant current, say, okay, what is Q basically? Q is what is current? Current is the rate of flow of charge, all right. So, if you are charging with a constant current I, okay, so it will take a time, say Td. Okay, all right. So, I into Td is that delta Q. Okay, if you are passing current I through Td, you require this. So the Td is the time required for the voltage across the capacitance to change by delta V, okay. And then from this you get Td is equal to C delta V by I, okay. That is very well known. That is, if you have a capacitance C charging through delta V with a constant current I, okay, you require time Td, okay. So which means that if you are increasing the current, it will take less time to charge, obviously, because basically this two product is equal to the charge you require, and so if I is more, Td will be less, okay. So this gives this part of the characteristic, okay. That is, if you are increasing I, it is going to fall, okay. But once you come to the when the other capacitance, the diffusion capacitance starts to dominate, okay, you will find that diffusion capacitance itself is proportional to current, okay. The junction capacitance is independent of current, so you get this type of relation, but the diffusion capacitance is itself proportional to current, okay, that CD, all right. So in this relation, Td will become independent of current, isn't it, if C is proportional to current, okay. So when the diffusion capacitance starts to dominate, okay, it becomes a constant. So you have this becomes independent of current, okay, all right. So okay, so what you have is, with current, initially the capacitance, the delay starts to fall with increasing current, all right, and then it becomes a constant, okay. That is, if you go on increasing the current further, there is no further increase in the delay, no further reduction in the delay, all right. So this is the minimum delay which you have, and it is determined by the diffusion capacitance or the stored charge effects in the device, okay. So similarly, also in an I squared L, if you plot the delay versus current, okay, that is the total injector current or the current you are feeding through the power supply, okay. If you are increasing that current, all right, you will get initially a reduction in delay and then it saturates, okay. So normally you would expect, you would operate the I squared L circuit in somewhere along this region, okay. That is, once you go to the minimum delay region, okay. Of course, there is no point in increasing the current any further, because what you are doing is you are not gaining in terms of speed, but you are increasing the power dissipation, okay. Of course, we have also seen that increasing the current increases noise margin. So there are other trade-offs also, okay. In fact, if you go on increasing the current too much, the delay goes up, okay. That is because of some other effects called high injection effects in bipolar transistors, okay, all right, which degrades the device operation, okay. So basically you have this type of curve for Td versus I, okay, all right. And if you want the power delay product, okay, the power delay product, power dissipation is given by I, if you want to say, okay, into nearly equal to delta V, okay. That is basically, if you assume that in saturation it goes very close to 0 volts, the transistor, okay, then the power delay product is equal to, and you are operating in this region, okay, where the junction capacitances dominate, you get something like C delta V squared, okay. Now this delta V is very small quantity in I squared L, okay, and power delay products, okay, are of as low as 0.1 picojoules, okay, can be very easily achieved, okay. So that is one plus point of I squared L. The power delay product in I squared L is quite low, but the problem is the delays are quite high. This minimum delay which you have, okay, from the normal structure is around, you cannot achieve something less than, it's usually around 10 nanoseconds or so. It is very difficult to go below that, okay, because of the excessive charge stored in the device, Okay. So, we shall look at it, okay, go back to the I squared L structure, okay, and now look at some modifications of the structure as such which has taken place from the technology point of view in order to improve this aspect, okay, that is the delay of that is the propagation delay, okay, of the I squared L cell. Okay. Okay. So, I will just draw the I squared L cell once more. Okay. So, this is the N region, N plus, and then you have the collectors. This is the base, okay, this is the injector, and then you have the N plus guard ring, all right. Okay. So, you have this is the injector contact, this is the base contact, this is the collector contact, and then you have the emitter contact from below. So, injector input, collector 1, say collector 2. Okay. This is the well known structure which we have been discussing. Again, just to draw the top view, okay, you have the injector, then you have the base, and you have the collectors, and these are the contacts. Okay. So, this is the injector contact, this is the input contact, these are the collector contacts. Okay. Now, as I was saying that the problem with I squared L is, see, there are a large number of areas where there you can have charge storage. Okay. For example, the emitter itself is lightly doped. Okay. So, with the result that you can have large charge storage in the emitter itself. Okay. Once it is lightly doped, you can have large minority carrier storage. Okay. All right, all this region. Okay. So, when this base emitter junction of the NPN transistor becomes forward bias, you have stored charge in the emitter. Normally, in a normal bipolar transistors, we do not talk of stored charge in the emitter because it is very heavily doped. Okay, Ni squared by N, it is proportional to that, so that is going to be low, but you are going to have large charge stored here. Also in the base regions, okay, you have a lot of extrinsic base area. Extrinsic base area means that is the areas which is not really a part of the transistor. See, we call this the intrinsic area. See, this is the NPN transistor, okay, where the transistor action is taking place. All right, this is the intrinsic area. Okay, this is the useful area of the device. Okay, the other regions, all right, here, okay, these are the extrinsic regions. Okay, this is the useful area again for this NPN transistor. But for the other regions, these are the extrinsic areas. These are parasitic areas which you cannot avoid, but you have a lot of stored charge there. Okay, here. Now, if you look at this structure, not only in between the transistors, you have all around the transistors. Okay. Okay, that is a top and bottom side of this NPN transistor. This is here. Okay. So, these are the extrinsic, you have a lot of extrinsic area, okay, and you have a charge stored here automatically when the device goes to forward bias, the junction goes to forward bias, okay. And so, when you have to switch off, you have to remove that excess charge, and it creates, gives rise to a lot of delay, okay, all right. So, that is the basic problem in the I squared L structure, okay, which gives rise to the poor performance in terms of propagation delay. In fact, if you draw the equivalent circuit of this particular structure, okay, the equivalent circuit would look like this. You have a PNP transistor, okay, and then you have this goes to the input contact. So this is the injector contact. Then this is the input side. Then this goes to the base, all right, of this NPN transistors. Okay. Now here you have series resistance. Okay, this is one transistor, say. Then you have another transistor, but again you have series resistance. All right. So this is collector 1, this is collector 2. Okay, this is the input. Okay, all right. Not only that, you have parasitic diode sitting here. Okay, these diodes, you see in these regions, this is a PN junction diode. Okay, so this is a PN junction diode here. Okay, all right. You not only have series resistance, say this is a series resistance here from here to here. Okay, there is a resistance from here to here. Okay, but you also have PN junctions here. All right. So whatever current flows in here, you know, part of it is getting wasted because of the PN junction here, and also you have series resistances. Okay, and also you have what is called the rail region. So this is this region just under the device. Okay, but you also have the rail region, that is this sides. Okay, I just marked with the color pencil, color chalk, these regions. Okay, this side and this side. Okay, the top and bottom. Okay, which is actually not contributing anything. So we can also draw, you know, the equivalent circuit like this. Another set of diodes. Okay. All right, and this is actually this is shorted here. So this is the contribution of the rail, what is called the rails. Okay, the rails are the sides. Okay. Okay. So this is the equivalent circuit of this cell. Okay. Now you see that because of these lot of parasitic elements, okay, there is going to be a lot of dissimilarity between this device and this device. Normally, even when we have obtained the condition for the proper operation of the I squared L cell, okay, what we did was we assumed that we have, when we have a multi-collector transistor, we assume that there are so many transistors in parallel, and there is all the transistors are similar. Okay, but you see that this transistor is not going to behave in a similar fashion as this transistor. Okay, it is going to have less base current compared to this transistor. Okay, so even though our analysis, okay, it should work through our analysis, but it may not work because this transistor may go to saturation, this collector may go to C1 may go to saturation, but the other transistor may not go to saturation. Okay, so this could be the problem. All right. So what do you do? So we have to look at how to eliminate these parasitic elements. Okay. Now the first thing which one can do is, in fact, came about with the proper isolation techniques, that is you use oxide isolation. Okay, that is silicon dioxide is used nowadays in semiconductor technology for isolation. Okay, that is isolating between individual devices or individual different areas on the semiconductor chip. Okay, that is one can remove this rail portion. Okay, that is basically you have a structure, okay, like this. I'm just drawing the top view. I think it will be clear. You have the P. So this is the PNP region, and these are the collectors. Okay, this is so this is one collector, this is another collector, this is the base contact. Okay, so this is the entire region is P, and this is the oxide region. This is oxide all round. So basically, if I draw the cross section across this region, okay, you have oxide, silicon dioxide, okay. Okay, so this is N. Okay, this is N plus. All right, wafer. You have P. This goes all the way. This is the base region. This is the collector, and this is the other collector. So this is the device. I hope it is clear. Oh, you have one more contact here, that is the injector contact. Okay. So this is the I squared L structure. Okay. So this is the oxide regions, isolating. Okay. It goes all around. So this is the base, these are the two collectors. Okay. Is it clear? It is almost identical to this, except what we have done here is, if I just modify this, okay, we have removed this portion, okay, just made this oxide, remove this portion, just made this oxide. Okay, it goes all the way here. Okay, I think that is the same as this. All right, and not only on this sides but also on the other side. Okay, this side also. Okay, what we have done is we have all this region, this entire region, this collector diffusion. Okay, is so this we have reduced the area up to here. Okay, and all around you have oxide. Okay, so we have removed a lot of this extrinsic area. Okay, these are the contacts. Is it clear? Okay, so that is going to help in one way. That is, all the extrinsic, a large portion of the extrinsic area has been removed. This side which you are having, okay, on the basically the rails have been totally removed. Okay. Now, so if in the equivalent circuit, what you will see is this portion has been totally removed. Okay. So we have sort of tried to improve the performance, but this in fact gives rise to some problems, extra problems. Okay. That is because if you look at the structure, original structure, okay, now the resistance. So for example, the resistance, okay, the series resistance for this particular device, say C2, okay, the current has to flow all the way here. Okay, there is a large series resistance. Okay, and if you have a transistor like this, okay, which regions is the series resistance going to be more? It is going to be under the collector diffusions. Okay, resistance is proportional to cross sectional area, isn't it? All right. So here you see, in this region, see basically the base width. This is the base width of the transistor. Okay, although it is not drawn to scale. So this is going to be very small. This is going to be a very narrow pinched region. Okay, and the current has to flow under this. Okay, to reach this transistor. Okay, so this resistance, this portion is going to be very high because of the very narrow region here. Okay, here of course again, since the cross sectional area is large, the resistance is smaller. Okay, if you look at the rail regions which we have eliminated, okay, in the rail regions you did not have any the current did not have to flow through any of these, under any of these collector diffusions, okay, the rail regions which we have eliminated, okay, all right. So the resistance, the rail resistance which we have in fact removed here, okay, that resistance is much less compared to these resistances, because here these resistances, the current has to flow under the collector diffusion areas, okay, where the cross sectional area is much less, okay. In the rail region you do not have any diffusion, the collector diffusion, so the cross sectional areas are much larger. So these resistance which were there, they were much lower resistance. So in fact if they were there, you know, the effective resistance for this is going to be less. So basically we have removed the low resistance path, so that is the problem. So again this did not really work out. So finally what came about was a self aligned I squared L process, okay, which I shall just we shall go through now, okay, which in fact removed most of these problems, okay. So I shall go through the process technology for the self aligned process, I squared L process, okay, and we shall then understand how it improved the device performance. Okay. So again in that self aligned process one uses oxide isolation, okay. So the first step is you define the active area, okay. Active area means where you want to make the I squared L cell, okay, and in the surrounding regions, okay, you have oxide isolate, silicon dioxide to isolate, okay. In fact you may have cells, you know, other cells also side by side, other active regions which are separated by these oxide, okay, silicon dioxide. So this is one active area, okay, in which you are going to make one cells, okay. So this is the top view. So if you look at the cross section, you have again the starting wafer is n on n plus n, and you have this is silicon dioxide surrounding the active region, okay. All right. The next step what we do is you grow oxide, silicon dioxide on top, okay, and then etch out, okay, leaving a certain region here, okay, which is going to be to separate the p plus p diffusion. So basically if you look at the mask, okay, on this, all right, you have a region like this, okay, all right. Okay, this is the on the top, looking from the top, the mask for p plus diffusion, and then what you do is you do boron diffusion, or basically implantation is done, okay, boron implantation through this mask. So here silicon dioxide protects this region when you do an implantation. So what you have is you have a p region here, okay, and another p region here, okay. These are the exposed regions, all right. So this is a p and this is the p. So you can identify that this is for the injector p diffusion and this is the base region for the NPN transistors, all right. So this is done. So I'll also write down the steps. So first is active area definition, then injector and base diffusion or implantation rather. Okay, so all right, this is done simultaneously, both is p region. Okay. Then what you have to do is we have to create the collectors. Okay. For that a technique which is used is polysilicon, okay, which is polycrystalline silicon, all right. This material is very interesting in the sense that it can be deposited on silicon at relatively low temperatures. Okay. Relatively low means around 600 degrees centigrade, okay, whereas most other processes are very usually take place at 1000 degrees, so even 600 degrees is considered low. Okay. So you can deposit silicon, polysilicon, and the advantage of polysilicon is that you can dope it also just like silicon, okay, and if it is very heavily doped, okay, with impurities, it behaves almost like a metal. Okay. That is, you know that in silicon, if the doping concentration is high, the resistivity is low. Okay. So if you make the doping concentration, the impurity concentration very high, okay, the resistance becomes very low, it behaves almost like a metal. Okay. So what is done is polysilicon is deposited, actually it is doped with arsenic, which is an N-type impurity. Okay. Polysilicon is deposited and again patterned, okay, and you have a pattern like this. I shall draw it here. Okay. So maybe these are the polysilicon regions. Okay. Okay. And from the mask, I just draw it like this, the top view, it looks something like this. Okay. So this is the top view and this is how it looks. So this is arsenic doped polysilicon, okay, which is N-type. Okay. Deposition of arsenic doped polysilicon, okay, and this is followed by what is called a drive-in. Okay. That is, this polysilicon consists of a lot of arsenic, which is an N-type impurity. Okay. Now, if you subject it to high temperature, okay, this arsenic, okay, it is going to diffuse into the silicon. Okay. It is diffusion is a process by which impurities move from a region of higher concentration to a region of lower concentration in this case. Okay. So this is full of arsenic, so it is going to move into the silicon, okay, and create an N region here. Just it is going to be self aligned in the sense it is going to be created just below the arsenic regions. Okay. All right. Now, the next step what is done is oxidation. Okay. You oxidize, okay, silicon plus in presence of oxygen, okay, it is going to be converted to silicon dioxide. Okay. So you create another region of wherever the exposed silicon is there, it is going to be converted to silicon dioxide. Okay. And polysilicon is also going to be converted to silicon dioxide. All right. This is a process of oxidation. Okay. But interesting property is that polysilicon oxidation rate is much higher than that of monocrystalline silicon here. Okay. So the oxide thickness on polysilicon is going to be much greater than on monocrystalline silicon. So you have, say, an oxide here, okay, but here it is going to be much thicker. All right. and then you have something like this, maybe here it is going to be much thicker. So you have silicon dioxide all over, okay. Here also you have, okay. So what you do is you oxidize and then you etch back the oxide, all right. You oxidize plus etch back. Then what is the advantage of this is, so you are doing oxidation and then you are etching back a part of that oxide. Now since, and you control that amount which you are etching back, okay. Now since the oxide thickness on polysilicon is more than that on this other regions, okay, once you etch back you will be left with some oxide covering the polysilicon, whereas in the other regions you have removed the oxide, extra oxide. Is it clear? All right. So basically what you will be left with is, you will be finally left with oxide covering for these polysilicon regions, and that is very important for this process. Okay. You understand? So what you have done is grown oxide and etched back, but you still retain some oxide on the polysilicon. Okay. So you have oxide here and here and here. Oxide, you know, silicon dioxide is an insulator. Okay. That is the important property of silicon dioxide which should be utilized here. Okay. All right. Now what do you do? So basically you did not require any mask here, okay, for this process. Now the next step is, what you do is, again you do a boron implantation. Boron, you know, is a p type impurity, okay. So once you do that on the exposed regions, okay, what you do is you make it p plus. Here the exposed regions is made p plus, heavily doped region, okay. The exposed regions which you have now are the extrinsic regions, okay. You see here the exposed regions, here it was going to become p plus also, okay. The and again you do not require a mask, okay. Whatever you are just doing a p plus implantation, here it is covered with silicon dioxide, nothing is happening. So only in the exposed regions you are covering, making it p plus. So what is the idea? The idea is, number one, you are going to reduce the series resistance. These p plus, these extrinsic regions are not taking part in any device action or device operation. So we must have to reduce the series resistance. Also, if you have a p plus region, the stored charge in those regions is going to be less. Okay, extrinsic region, the stored charge is less, must be reduced, okay, and p plus, the stored charge is going to be less, because again the stored charge is proportional to Ni squared by n, you know. So okay, so automatically these regions becomes p plus, whereas under the collector it is still p, okay, it is only in these regions. And then what you do is you do the metallization. Okay. Now you have another mask, okay. I hope, yeah. So this is, I think this will be more visible, it's okay. So this is one region, okay, and another mask from right from here to here, okay. This actually goes out from here, okay. So this entire region you deposit the metal, okay. All right. So what happens in the cross sectional view, okay, you have metal like this, okay, and then you have metal going from here, all the way, Okay. So this becomes the injector contact. Okay. The base contact you can take from somewhere here maybe, and the individual collector contacts, okay, is actually taken from here, somewhere here, it goes there, you know. Okay, you cannot along this you cannot show because it is covered. Okay, so this the collectors. Okay, it goes this way from the top view. Okay, you can take the contact from somewhere here. Okay, now see what you have achieved. See, this is the collector. Okay, this polysilicon itself is acting as the contact. Okay, much in the same way as in a MOSFET technology you have poly gates. Okay, you have the polysilicon acting as the gate material as well as for metal lines. Okay, so this is the collector contact taken through the polysilicon. It goes this way, all right, and this is the base contact. Okay, now what is happening is, see, this is the base. It is the base contact is here. It comes and it makes contact here also. All right, it makes contact here also. But because of the intermediate oxide region, the collector and the base are not shorted. Okay, the collector has a covering of silicon dioxide which acts as an insulator. Okay, now what you have done is you have basically shorted the base here as well as here as well as here. Okay, and you have intermediate P plus region. So all these regions, these resistances are basically shorted out because you have a contact here, and this is, okay, in the equivalent circuit here. Okay, this and this has been shorted. Okay, this has been shorted. Okay, all the base regions, even if you have 3 or 4 collectors, okay, no, all the regions will be shorted, and this is P plus. Okay, so the resistance, series resistance, okay, to this region is going to be very small because of the P plus in the extrinsic regions. Okay, so this is the final structure you have. Okay, so you have the injector contact, the base contact, and the collector contact taken out. So this is a self-aligned process, okay, where the self-aligning means you have done a lot of processes without actually having to align, because all these regions, the extrinsic regions and the collector, okay, they are all aligned by themselves with respect to each other almost automatically. Okay, and for that reason you don't require, when you have to do an alignment, you always have to maintain a tolerance. Okay, so that increases the area, but here, because of the fact that you have it self aligned, the area requirement is much less. So boron implantation, this is where we had stopped, and then metallization, I think. So that would complete the process. Okay, so this is the self-aligned I squared L process, and you see that this is of course much superior compared to the previous thing, equivalent circuit wise also. Okay, a lot of the parasitics are basically getting removed, and these diodes also, is the charge stored in these diodes would be much less, like the extrinsic regions, because of the P plus doping, okay, in the extrinsic regions. All right. Okay. So this particular structure was actually proposed in around 1980, I think, and came out in a paper. And of course, it was far superior to the other technologies. Okay, the results I shall give you the reference also, just if you want to go through it. It is et al. Others, IEEE transactions on electron devices, page 1379 to 1384, 1980. Okay, and the results which they came out was for a fan out of 3 for this particular structure. Okay, for fan out equal to 3, that is for 3 collectors. Okay, they had a beta effective equal to 4, and interestingly the propagation delay of 0.8 nanoseconds. Okay, all right, at a collector current of I naught equal to 100 microampere. So propagation delay, so power delay product was 30 femtojoule. Okay, so you see that of course it is very remarkable results. Okay, so much better than the previous results. Okay, so this is really sub-nanosecond device. Okay, in fact, later on, still further improvements have been made in technology, which makes it very complicated, in fact, and most of the simplicity inherent in I²L structure, that has been lost. But it has been in 1985 there was another paper, okay, by another group, which achieved 290 picoseconds per gate delay. Okay, so that was the that is, I think, and a power delay product and power delay product of 15 femtojoule. Okay, so this is by far the best results which have been reported, okay, for I²L. Okay, it's quite good, for silicon I²L. Okay, there presently a lot of work is going on in I²L made out of heterojunctions. Okay, I shall take that up sometime later, a few classes later. Okay, because I have to introduce the advantages of heterojunctions. Okay, and heterojunction I²L, okay, the delays have been even less than 100 picoseconds. Okay, and in fact that is the area where a lot of work is going on in I²L, okay, rather than silicon I²L presently. And in fact even microprocessors have been Texas Instruments have fabricated a microprocessor using heterostructure I²L. Okay, so we shall go to that, okay, later on. But this is the present condition, okay, the delays, okay, which has been achieved using I²L. Okay, the next we shall take up the next class some special I²L structures or some special modifications of I²L, and then we shall actually go into heterostructure I²L and see the latest performance before we wind up the topic of I²L and go on to next other logic families.